students, welcome to this lecture. In this lecture we will continue our study of finding series solutions for linear differential equation in the neighborhood of regular singular point. So, if you recall, in previous lecture we have discussed the method of Frobenius to find out series solutions for linear differential equation, and we have considered basically 3 cases depending on the roots of initial equation. So, in case when roots of initial equation are not equal and not differ by a integer, we know how to find out the solutions, and that we have discussed in previous class. Now, in this class we discuss the case when the roots of initial equation say E are equal, and we have seen in previous class that when roots of initial equation, here it is denoted as R1 and R2, and when R1 is equal to R2, and we have only one solution of the form, that is y1 t equal to t to power r1 summation n from 0 to infinity a n t to power n. So, one solution is given like this, and the second linearly independent solution is given by this y2 t equal to y1 ln t plus n equal to 0 to infinity a n dash r1 t to power n plus r here. So, here this is basically r1 here. So, here this the solution, this the current form is already discussed in previous class. Here we take some example based on this. So, here let us take one example. So, find two solutions of Bessel's equation of order 0. So, here Bessel's equation is given by t square d2y by dt square plus t dy by dt plus t square y equal to 0, t greater than 0, and we look at that if you look at the coefficient of d2y by dt square, that is t square. So, t equal to 0 is a singular point, and now we want to check whether it is a regular singular point or irregular singular point. Now, we want to show that it is a regular singular point. For that, look at the TPT. So, TPT is 1 and t square qt is 1. So, both are in basically constant function. So, we can say that both are analytic function near t equal to 0. So, it means that our theory can be applied here to find out a solution. So, here let us assume yt equal to summation n equal to 0 to infinity a n t to power n plus r is a proposed solution, and we need to find out the values of r and the corresponding coefficients a n's, so that this will serve as a solution of equation number 3. So, for that you just calculate y dash t. So, y dash t is from n equal to 0 to infinity n plus r a n t to power n plus r minus 1, and calculate y double dash t. So, it is n equal to 0 to infinity n plus r into n plus r minus 1 a n t to power n plus r minus 2. So, once we have y t, y dash t, y double dash t, put it back to equation number 3, and you will see that here it is n equal to 0 to infinity n plus r into n plus r minus 1 a n t to power n plus r, because here we have already term like t square. So, t to power n plus r minus 2 into t square will make it t to power n plus r, plus here it is t dy by dt. So, here it is summation n equal to 0 to infinity n plus r a n t to power n plus r plus n equal to 0 to infinity a n t to power n plus r plus 2. So, here it is t square y is already given to you. So, you can write n equal to 0 to infinity a n t to power n plus r. So, here we have the Ly equal to n equal to 0 to infinity n plus r minus 1 a n t to power n plus r plus n equal to 0 to infinity n plus r a n t to power n plus r plus n equal to 0 to infinity a n t to power n plus r plus 2. Once we have this equation, then we do the equating the sums of like powers of t equal to 0 here. So, here if you look at, when you put n equal to 0, your powers will start from 2, and if you look at the first two terms, if you start put n equal to 0 to then your powers start from t to power r. So, we can collect the coefficient of t to power r and t to power r plus 1 and t to the power r plus 2, then all the terms of this equation will come into picture. So, first let us look at the coefficient of t to the power r equal to 0. So, t to power r equal to 0 means here look at the first term, here you put n equal to 0. So, it is r into r minus 1 plus here you will also get r. So, it is r into r minus 1 plus r, that is r square a naught. So, this we write f of r a naught equal to 0. So, this is corresponding to t to power r, and here we are getting this r into r minus 1 a naught plus from second term we are getting r a naught and the equal to 0, because here if you look at in third term, if you put n equal to 0 then the power is t to power r plus 2. So, there is no contribution from the third term. Okay. So, here we have t to power r and we have this r square a naught, and that is f of r a naught equal to 0. And then you look at the coefficient of t to power r plus 1, again there is only contribution from first two term only, that is corresponding to n equal to 1. So, it is r plus 1 r a 1 plus r plus 1 a 1 equal to 0. So, if you calculate this, then here we have 1 plus r whole square into a 1, which I am writing as f 1 plus r a 1 equal to 0. And then when you put general term t to power n plus r equal to 0, then what you will get here is from this term, so write general term. So, it is n plus r minus 1 a n plus n plus r a n, and if you look at the last term, then last term is having power t to power n plus r plus 2. So, if we replace n by n minus 2, then that power will be t to power n plus r. So, here we write a n minus 2, and that is the coefficient of t to power n plus r. So, if you simplify this and this will give you n plus r whole square a n. So, here you will get as n plus r whole square a n equal to minus of a n minus 2 here, that we are writing it here. So, so here we will get three equations. First is r square a naught equal to 0, and then next is f of 1 plus r into a 1 equal to 0, and last one is f of n plus r a n equal to minus a n minus 2, and here n is greater than or equal to 2. So, now so equation 1 is the initial equation, and that is r square a naught equal to 0. So, and we already know that a naught is never 0. So, your initial equation f of r is equal to r square equal to 0. So, if you look at the roots of this initial equation are 0. So, r1 equal to r2 equal to 0. So, here we have a equal root of initial equation. Now, if you look at the second equation, that is r plus 1 whole square a 1 equal to 0. So, if you take r equal to 0, then this term is non-zero. So, a 1 has to be 0. So, from second equation we say that a 1 has to be 0, and if you look at the third term, that is f of n plus r, here okay. So, last one is what, f of n plus r a n equal to minus a n minus 2. So, here we can write a n as minus a n minus 2 upon n plus r whole square, and that is n greater than or equal to 2. So, for we have equation like this, a n equal to minus a n minus 2 divided by n plus r whole square and n greater than or equal to 2. Now, we already know that a 1 is 0, that we have just calculated, a 1 equal to 0. So, using this formula we can say that all the odd terms are going to be 0, because if you write a 3, then a 3 is given in terms of a 1 minus a 1 upon 1 plus r whole square. So, here we say that since a 1 is 0, so a 3 is going to be 0. Now, a 3 is 0, then using this recurrence relation we can say that all the odd terms are going to be 0. So, so that fixes the matter that all the odd coefficients are 0. Now, look at the a2r. a2r is given as using this formula 4. a2r is equal to minus a naught upon 2 plus r whole square, and here we write minus 1 upon 2 plus r whole square into a naught. Now, if you look at a4r is equal to minus a2 upon 4 plus r whole square. Now, a2 we have already calculated, so it is 1 upon 2 plus r square and 4 plus r square a naught, and so on. So, in this way we can calculate our even coefficient, even order coefficients, and we can write this formula as a2n_r equal to minus 1 to power n 2 plus r whole square 4 plus r whole square and so on 2n plus r whole square into a naught. And to determine y1t, we simply put r equal to 0, because here we have two roots, r1 equal to 0 equal to r2. So to find out one solution, we can put r equal to 0, and we can find out a2 0 equal to minus 1 to power n, and when put r equal to 0, all these terms will be sample vanishing. So it is 2 square 4 square and so on. So a2n 0 is going to be 2 square 4 square up to 2n whole square. So or we can write it a2 as minus 1 to power n 2 square a naught, and a40 as 1 upon 2 square 4 square a naught and so on. So in this way you can calculate here a2n0 is equal to here minus 1 to power n, and if you look at it is 2 square 4 square and so on n square, and if you simplify it is an a naught, and it is simply minus 1 to power n, and here if we look at it is what 2 4 6 and so on 2n, here it is 2n whole square and whole square, and this we can write as minus 1 to power n 2 to power 2n into factorial n whole square. Here that we can simplify here we can, if we take 2 out, then it is 1 2 3 and up to n. So here we can write minus 1 to power n and 2 to power here 2n will come out and factorial n whole square. So that we are n into a naught we are writing here. So here we got a2n0 as minus 1 to power n a naught divided by 2 to power 2n factorial n whole square. So now we can we already know that all odd terms are 0, so we can write y1t as 1 minus you simply write it y1t equal to summation a n t to power n plus r, n is from 0 to infinity. So here this we can write as, let me write it here. So here we can write a naught t to power r plus a1 t to power r plus 1 plus a2 t to power r plus 2 and so on. Now we already know that these terms are gone, odd terms are gone, so and r equal to 0 here. So we can write a naught, let us say that if we take a naught as 1, then we can write our solution as y1t equal to 1 minus t square upon 2 whole square. Here we are using the value of a2, that is value of a2 we have already calculated, value of a2 is minus 1 upon 2 square. So here we are using 1 minus t square upon 2 square plus a4 as 1 upon 2 to the power 4 factorial 2 whole square and so on. So in this way we can calculate y1t. So y1t is one solution of 3 that we have already calculated, and this solution is referred as Bessel's function of the first kind of order 0, and we denote as 0 t. So now to obtain a second solution, we have already seen that our second solution y2t can be written as y1t into ln modulus t plus n equal to 0 to infinity a dash 2n 0 t to the power 2n. Here I am writing a 2n dash 0 because we already know that a 2n plus 1 r is 0 irrespective of whatever value we in the n. So here what is left out is only the even terms. So here we need to calculate the derivative of a 2n r. So for to calculate derivative of a 2n 0, so here we use this thing. We already calculated a 2n r like this. So here let us assume without loss of generality that a naught is equal to 1, right. Then a 2n r is given by this, and if you want to calculate a dash 2n at 0, for that we simply look at that a dash 2n 0 divided by a 2n 0, that can be written as d by dr ln of a 2n r modulus of modulus of a 2n r log, and that you calculate at r equal to 0, and we using the, let me do it here. So here a 2n r is given as minus 1 to power n. It is I think it is written here. It is 2 plus r whole square, let me write it here, 2 plus r whole square, 4 plus r whole square, and so on, 2n plus r whole square. So, here let us take the modulus of a to n r, that is that will get rid of this minus sign. So, it is 1 upon 2 plus r whole square, 4 plus r whole square, and so on, 2n plus r whole square, and then take the log ln. So, here if we take the ln here, then it is what, ln of minus 1, that is going. So, minus ln of the summation will come, sorry, this summation is outside this. So, here you will get summation L, here we can write 2 plus r 2n plus r whole square, n is from 1 to sorry, if we write k. So, let me write it k here, to k plus r, k is from 1 to n. So, we can write ln of modulus of a to n r equal to minus of k equal to 0 to n ln of 2 k plus r whole square. Is it okay? Then we can take the differentiation. So, if we take ln of modulus of a to n r, now we take the derivative. So, derivative will be 1 upon a to n r and a dash to n, and here it is r. Now, we take r equal to 0 here, equal to, here it is what, minus, and then we can summation k equal to 0 to n, and 2 you can take it out, 2, and this is 1 upon 2 k plus r, and k is from 0 to infinity, and that you calculate at r equal to 0. So, when you simplify, you write, sorry, it is k equal to 1, not 0. So, it is from k equal to 1. So, here when you put it is what, minus, and here when you put k equal to 1, then it is what, 1 upon r, 1 upon 2 is already out, minus 2, and here it is what, 2 plus 1 upon 4 plus so on. So, you will get, and when you take 2 out, then it is what, it is given as minus 1 plus 1 by 2 plus 1 by 3, and last is 1 by n. So, here we can get this as a dash to n 0 divided by a to n 0, like this, and this we denote as Hn. So, that we are going to write it like this. So, here we have calculated a dash to n 0 divided by a to n 0 as minus 2, 1 upon 2 plus r plus 1 upon 4 plus r, and so on, and when you put r equal to 0, then all these term will simple cancel out, and you take 2 inside, then a dash to n 0 is equal to minus 2, 1 by 2 plus 1 by 4, and so on, a to n 0. Now, this I am writing as minus 1 plus 1 by 2 plus 1 by 3, and so on, a to n 0. So, here if we set the bracket term as Hn, so we can write Hn as 1 plus 1 by 2 plus 1 by 3 plus 1 by n, then we can write a dash to n 0 is equal to minus Hn into minus 1 to power n divided by 2 to power 2n factorial n whole square. This we are writing as the value of a to n 0, that is minus 1 to power n divided by 2 to power 2n factorial n whole square. So, using the value of a to n 0, we can write a dash to n 0 as this. So, y to t is equal to y1 t ln mod t plus n equal to 0 to infinity minus 1 to power n plus 1 Hn t to power 2n divided by 2 to power 2n factorial n whole square, and that is going to be your second solution of Bessel's equation of order 0. But if you look at here, this Bessel's second solution contains the term ln modulus t, and because of this it is having unboundedness near the point t equal to 0. So, generally we ignore this second solution, but for sake of completeness we are putting the second solution like this. Okay. So, now look at the last case, the second case where the method of Frobenius may not give the second solution of the Frobenius form, and this occurs when the roots of the initial equation differ by an integer. So, here we have already seen that when R1 minus R2 is non-zero and not integer, then we already know that we have discussed in first previous lecture, and the case when R1 equal to R2, that is difference is 0, we have already discussed one example right now. And then last case when R1 minus R2 is equal to some n, where n is some integer, that we want to discuss it now. So, here we already assume that R1 is greater than R2. So, let us take R1 equal to R2 plus some n naught is some integer, positive integer, and in this case also we have only one solution of the form, that is y1 t equal to t to power R1 summation n equal to 0 to infinity a n t to power n, and we are not sure about the second solution. Why? Because we are going to discuss, but we are not sure about the second solution will take this form or not. It may take this form, it may not take the this particular form, that depend on the difference of R1 minus R2. So, here we will not get the second solution, because if you look remember the recurrence relation is what? F of R2 plus n into n plus R2 equal to minus summation k equal to 0 to n naught minus 1, and this term is there. So, from recurrence relation we know that if f of R2 plus n equal to 0 when n is equal to n naught. So, when n equal to n naught, then the coefficient of a n naught is basically 0. So, here this is 0, and here if you look at the right hand side, it is minus k from 0 to n naught minus 1, k plus r 2 p n naught minus k plus q n naught minus k into a k. That is, I am writing the recurrence relation for n equal to capital N naught, and we cannot find the coefficient a n naught if the right hand side is non-zero. So, if right hand side is non-zero, then this equation cannot be satisfied. So, it means that in this case, when this right hand side is non-zero, we do not have any solution of the form given by Frobenius. So, in this case equation 3 has a second solution of this form, y2 t equal to y1 t ln t into some constant plus t to power R2 summation n equal to 0 to infinity Bn Tn. So, it is up to us how to calculate this Bn and this constant. So, many times it may happen that your constant k may be 0. So, in second solution may happen that we do not have a term involving ln t, but that will depend how to find out this k and Bn, and one method to find out this is the method of variation of parameters. So, once we know one solution, we can use method of variation of parameter to find out the other solution. So, it means that when this right hand side is non-zero, then we do not have say no method to find out this coefficient a n naught, and we simply say that second solution will not be the form of Frobenius series solution, and it will take the form of 8, where it may or may not involve the term y1 t ln t, and it is up to us how to calculate this Bn. So, but if this is 0, means if the right hand side of this equation is 0, then of course we can say that here that equation is satisfied, means 0 into a n naught equal to this term which is already equal to 0. In this case we can choose any value of the coefficient a naught. So, in particular we will take the value 0. So, here we take a n naught as 0 value. If we take a non-zero value, then we will get a part of y1 t. It means that when we take in a n naught as non-zero, then when you calculate all the coefficient and when you write the general solution, then you will see that y2 will contain a part of y1 t. So, to avoid this thing, we generally assume that a n naught is equal to 0. So, here we say that once we have a and naught, then we can use our recurrence relation to find out the further coefficients a and naught plus 1 and so on. So, in this case when this right hand side is equal to 0, we can find out all the coefficient, and we say that our solution is given in terms of series solution of the form of given by Frobenius. So, let us take one example based on this thing that root differ by integer. So, here let us take Bessel's equation of order 1 by 2. So, here it is t square d2y by dt square plus t dy by dt plus t square minus 1 by 4 y equal to 0. Here I am assuming that t is positive. So, here we can easily see that t equal to 0 is a regular singular point, as pt is equal to 1 by t and qt is equal to 1 upon t square into t square minus 1 by 4 are not continuous at t equal to 0. So, that first thing is to check whether it is a singular point or not. So, once it is singular point, then look at the next thing, that is it is a regular singular point or not. For that you look at tpt and t square qt. So, look at tpt is equal to 1 and t square qt is t square minus 1 by 4, and we can say that these two are analytic functions. So, we can say that t equal to 0 is a regular singular point. Then once it is a regular singular point, then we can propose our solution is of the form yt equal to summation n equal to 0 to infinity a n t to the power n plus r, and we can find out the solution y dash t equal to n from 0 to infinity n plus r a n t to the power n plus r minus 1, and y double dash t equal to n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r minus 2. Put it back to equation number 10, and we can have Ly as summation n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r, because t square is already there, and second term is n equal to 0 to infinity n plus r a n t to the power n plus r plus n plus 0 to infinity a n t to the power n plus r minus r plus 2 minus 1 by 4 n equal to 0 to infinity a n t to the power n plus r. So, last two term is corresponding to this term, that t square minus 1 by 4 into y. So, when you simplify this, we simply say that this term and the last term will give you the coefficient of t to the power n plus r, and this term means third term is going to give a term having power t to the power n plus r plus 2. So, we can write this as from n equal to 0 to infinity n plus r into n plus r minus 1 plus n plus r minus 1 by 4 a n t to the power n plus r, and from n equal to 2 to infinity a n minus 2 t to the power n plus r. So, again this we can simplify, and we can say that it is n plus r whole square. So, we can write that equating the sums of like powers of t equal to 0. So, here we first let us take t to the power r. If you look at the coefficient of t to the power r, that we can obtain from by putting n equal to 0. When put n equal to 0, then it is r into r minus 1 plus r minus 1 by 4. So, it is r square minus 1 by 4 r square minus 1 by 4 into a naught equal to 0. And when you look at t to the power r plus 1, and then again there is no contribution from this term, and we will look at here by putting n equal to 1. When you put n equal to 1, then we get 1 plus r minus 1 plus 1 plus r minus 1 by 4 a1 equal to 0. So, we have f of 1 plus r a1 equal to 0, and f of 1 plus r is 1 plus r whole square minus 1 by 4 a1 equal to 0, and last is t to the power n plus r, and here we have f of n plus r a n, which is given as n plus r whole square minus 1 by 4 a n, and there is a contribution of last term also. Here it is plus a n minus 2. So, here when you take the other side, it is minus a n minus 2. So, here we will get these three equations. First will give you first is the initial equation, which will give you the values of r for which we can find out the solution, and that when you look at it is nothing but r equal to plus minus 1 by 2. So, r1 is the bigger value, that is 1 by 2, and r2 is equal to minus 1 by 2. So, here we have two initial roots of initial equation which are different, which are differed by an positive integer, that is 1. So, let us look at the analysis of this. So, here we as I said that R 1 is equal to 1 by 2, R 2 is equal to minus 1 by 2. So, let us find out the solution corresponding to R 1 equal to 1 by 2, and let us set that A naught equal to 1, so that this solution should not come again. So, now look at the second solution, and if you put R equal to half, then what you will get here, when you put R equal to half, then you can say that this term is not going to be 0. So, A 1 has to be 0 for this. So, here we say that second equation forces A 1 to be 0. So, we can say that since A 1 equal to 0, then by recurrence relation, that is obtained by the last equation, that is this thing. So, here we can simply say that A n equal to minus A n minus 2, and if you simplify, this is what, n plus R whole square minus 1 by 4, and when R is equal to half, when you can simply say that A n equal to minus A n minus 2, and here it is what, n plus half whole square minus 1 by 4. You can further simplify this. Okay, so we can write A n as minus A n minus 2 divided by n plus R whole square minus 1 by 4. So, from this we can simply say that since A 1 is equal to 0, then all term will be 0. So, then even coefficient we need to calculate. So, let us calculate A 2 R. A 2 R is equal to minus A naught upon 2 plus R whole square minus 1 by 4, and we can simply say that it is minus 1 upon 2 plus R whole square minus 1 by 4, and similarly we can calculate A 4 R and all that. And we can prove by induction that A 2 and R is given by minus 1 to power n, 2 plus R whole square minus 1 by 4, 4 plus R whole square minus 1 by 4, and so on. So, this is the formula of A 2 and R when R is some values. Now, we already know that our first solution is corresponding to R 1 equal to 1 by 2. Just put the value of R 1 equal to 1 by 2 and put set equal to A naught equal to 1. We can say that this equation is given like this. So, here we have A 2 as minus 1 upon factorial 3, A 4 as 1 upon factorial 5. You can simply calculate A 4 as minus A 2 upon 4 plus 1 by 2 whole square minus 1 by 4, and we can write it like this. In fact, you can use the formula of A square minus B square as A minus B, A plus B. So, we can say that here it is 2 into 3, in A 2 it is minus A naught upon 2 into 3, A naught is 1. So, we can write minus 1 upon factorial 3, and A 4 it is what, minus A 2 upon 4 plus half whole square minus 1 by 4, which we simplify and we can write it 1 by factorial 5, and so on. So, here we can prove by induction that A 2 n is going to be minus 1 to power n divided by factorial 2 n into 2 n plus 1, that you can prove it. And once we have A 2 n, we can easily find out the first solution, y 1 t as t to power r, then it is t to power 1 by 2 n upon t minus t cube upon factorial 3, and so on. So, by plugging, let me write it here, y 1 t equal to t to power r 1 summation a 2 n r 1 t to power 2 n, and is from 1 to infinity. Basically it is from 0 to infinity, and A 0 we are assuming as 1. So, that we are writing it here. So, we are writing y 1 t is equal to t to power, so r 1 is half here. So, here we have already calculated A 2 n as minus 1 to power n divided by factorial 2 n plus 1. So, we can write down our solution as y 1 t equal to t to power r 1 summation n equal to 0 to infinity A 2 n r 1 t to power 2 n. So, here A naught is already we assumed as it is 1, and r 1 is equal to half, then we can put as root t into A naught, that is 1, and A 1 is 0. So, that we are cancelling out. A 2 we have calculated as minus 1 upon factorial 3. So, t square plus A 4 is 1 upon factorial 5 into t to power 4 minus and so on. So, now if you look at this, then we can multiply and divide by t. So, we can multiply it by t here. So, we can write this as t to power half divided by t, and in the bracket it is t minus t cube upon factorial 3 plus t 5 upon factorial 5, and so on. And we already know that this is an expansion of sine series, and we can write this as t half divided by t is 1 by root t, and this is sine t. So, y 1 t is given as 1 upon root 2 sine t. So, that is our one solution, and we can find out the other solution. Look at the other solution here, but so it means that in this case our one solution is given by 1 by root t sine of t, and we try to find out, and if you look at in this case r1 minus r2 is basically 1. So, we need to find out our second solution. The second solution may not be of this form, maybe some other form. Let us look at this analysis, and that analysis we are going to do in a next lecture. So, here we conclude and we will discuss it in next lecture. Thank you for listening us. Thank you.